Hey math fans, Alex here, and in the last video I kind of talked about a lot of elements of set theory, and I ended with a couple of exercises to have you visualize some facts, including these two, which are kind of precursors to what I'm going to prove today, which are DeMorgan's laws. So first up, let's see if we can visualize both of these with a Venn diagram. Okay, so imagine that I have a sample space here with two sets, which we'll call A1 and A2. And the first fact says that the complement of their union is equal to the intersection of their complements. What on earth does that even mean? Well, the union, remember, is all of A1, A2, and their intersection. So if I were to shade that, it would just be all of this. So then the complement is really everything else. Okay, so it's going to be everything else, not including any of the Venn diagram. Okay, so that's the complement of A1 union A2. So that's this part right here. Now that is presumably equal to the intersection of the complements of A1 and A2. Well, let's just go ahead and shade both of those. Try to do them in different colors. Okay, so the complement of A1 is everything that's not in A1. Okay, so that is, I'm just going to draw like a circle around the circle and then expand. That is everything else. Okay, and then the complement of A2 is going to be, again, I'm going to draw a circle around this. Everything that's not in there. And you'll see that the intersection of those two quantities is really just the orange shaded region, right? It's definitely not this, because that's not in A1 complement. It's definitely not this, because that's not an A2 complement. And this is in neither. So it has to be everything else, which was precisely this. Okay? And likewise, you can prove the other statement very similarly. Okay, so hopefully that kind of makes sense. But how do we arrange a proof using set theory? Well, that's what we're going to talk about now. Okay, so I'm only going to do part of this proof. I'm really just going to choose one direction. We're going to kind of go with that. Okay? So we're going to start maybe with proving number one. So we're going to do a proof of number one, which, remember, says that the complement of the union is equal to the intersection of the complements. So how on earth do we prove that? Well, to prove that two sets are equivalent, you have to show that everything in the first set is in the second set, and everything in the second set is in the first set. So the way that we typically do these proofs is we start off by letting X be in the thing on the left, which is a set. And then somehow we have to show that X is also in here. Okay, so X is going to be in some really complicated mess, but the important part to note is that X is going to be in something complement. It's going to be in the complement of some set. Well, then by definition, if X is in the complement of this, that means X is not in this, which means it's not in the union of A1 and A2. Well, think about this. Again, you can draw a Venn diagram as you're doing these, but if X is not in this union, that means it's not in A1 and it's not in A2. Okay, remember the union says it's in A1 or A2. If you're saying it's not in A1 or A2, that means, hey, I'm not in A1 and I'm not in A2. So we have that X is not in A1 and X is not in A2. Okay, that and is going to be important. What now? Well, if x is not an A1, so since x is not an A1, x must be in the complement to A1. And since x is not an A2, x has to be in the complement of A2. Okay, so there's that word and again. We have that x is in the complement of A1 and x is in the complement of A2. So then x must be in A1 and x is in A2 complement. So we have that x has to be in the intersection of both A1 complement and A2 complement. And then we're done. We just showed that if x is in here, it must be in here. Okay, so I call that done with that part. So really, we call this the forward direction. Why do we call that the forward direction? Because we're starting with the assumption that x is in here, and we just showed that it was in here. Now we have to go backwards. Okay, so this is going to be the backwards direction. Now, let x be an element of A1 complement intersect A2 complement. And you should be able to do the exact same argument in line of reasoning to show that x must be in the complement of the union. Okay, but I will go through it nonetheless. So if x is in the intersection of A1 complement and A2 complement, I'm going to go a little faster this time. Then x is in A1 complement and x is in A2 complement. So if x is in A1 complement, that means x is not in A1. And if x is in A2 complement, that means that x is not in A2. Okay, but if x is not in A1 and x is not in A2, that means it's in neither A1 nor A2. Okay, but that nor or means that x is not in A1 or A2. Okay, so this means that x is not in A1 or A2, which is the same thing as saying it's not in the union. Okay. But if it's not in something, that means that it's in its complement. So it's in A1 or A2 complement. It's in the union complement. Okay. And then we're done. We just proved the first claim. The second claim I'll leave up to you to prove. We're really going to start generalizing now and actually talk about DeMorgan's laws. And I'm going to prove something very similar to number 2. Right? All right, so here are DeMorgan's laws. They look more complicated than they are. If you understood it for 2 sets, then this is just an extension of that. The only extension is that it could be in more than 2 sets. It could be in 3 or 4, or it could really be an accountably infinite number of these sets. So the way that we denote that, because I can't very well just say A1 union, A2 union, A3 union, A4 union, and I can't just keep doing that forever. So instead of 1, 2, 3, 4, we just put all of those numbers in a different set called the indexing set. And for some indexing set I, which is either finite or countably infinite, consider the family of sets A sub k, where k is an I. Okay, so note that this just means, you know, A1, A2, A3, and possibly so on for forever. Okay, then we have the following results. We have that the complement of the union is still the intersection of each of the complements. And likewise, we have the complement of the intersection equal to the union of each of the complements. Okay, so note that for k equals, or I guess for I equal to the set 1 and 2, this reduces back to what we had above, because then we're just talking about sets A1 and A2. Okay, but this is a really powerful generalization, so I'm actually going to go ahead and prove number 2, because it mirrors above what I didn't prove. I didn't prove this one, so now I'm going to kind of mirror that with DeMorgan's. All right, let's get started. Proof of 2. So again, we're going to have a forward direction and a backwards direction. So for the forward direction, let x be an element of the complement of the intersection of all such a sub k's. Again, what's the big picture happening? The big picture is that x is an element of some complement. That means that x is not in the original set, which is an intersection. Then let's think about it. If x is not in all of these, then there has to be at least one a sub k for which it's not a member of. Maybe it's just one that it's not a member of. Maybe it's not a member of all of them. We don't know, but we do know that if it's not in all of them, it's not in at least one of them. Okay, so this means that really there exists k in I such that x is not in a sub k. It's not in at least one of them. Okay. If x is not an element of a sub k, then x is an element of its complement. And if it's an element of this complement, let's just think this through for a second. Let's suppose that x was an element of maybe, I don't know, some set we'll call k. Well, if x is an element of that, surely that implies that x is an element of either k or L, because it's at least an element of k, so it satisfies that. Okay, so by the exact same condition, if x is an element of the complement of one of the a sub k's, then it follows that x has to be a member of the union of all of the a sub k complements for all of them, because we know that it's an element of at least one of them. Okay, and then we proved that because we showed an element in here is an element in here. So that's the forward direction. Okay, as for the backwards direction, just have to let x be an element now of the union. And then this is going to be very similar. Okay, so if an x is an element of the union of all the complements, okay, then x is an element of at least one of them for some k and I, the indexing set. It's an element of one of the complements. Okay. Which means that x is not in a sub k. For some k in I. Well, if it's not in a sub k, then it's not in all of them. Clearly, if x is not a member of one set, we'll call it maybe if x isn't in k, then clearly x is not going to be in k intersected with L, because that requires it to be an element of both of them. Okay, but this implies it implies that x is not going to be an element of all, or the intersection of all a sub k's. So we have that x, if it's not in something, that means it is in the complement. Just put a bar, and then we're done with that part of DeMorgan's laws. Now, as an exercise, you should rewatch this video and try to prove number 2 for the case of 2 sets. And you should try to prove number 1 for DeMorgan's laws. You really have everything that you need. I proved both of them in some capacity. You just have to fill in the details for the rest.